Welcome back to our series on electricity and magnetism. In this episode, we're going to talk about induction. Namely, we're going to look at Faraday's law and its associated Lenz's law, which is going to complete the second half of electromagnetism for us. We've already seen how a current flow can cause the formation of a magnetic field. And now we're going to complete that circle and look at how a magnetic field, namely a changing magnetic field, can induce a current flow. This all happens through the concept of magnetic flux. Well, if we think back to electrical flux, we'll notice that magnetic flux is calculated in exactly the same way. We even use the same symbol, capital Phi. And of course, it's going to be the integral of B, the magnetic field, dotted with dA. In essence, this is like taking an area, placing it in a region where there's a magnetic field, and then measuring the degree to which the magnetic field passes through that area. Because it's a dot product, we're really interested in the degree to which the magnetic field is parallel to the area vector. And keep in mind that the magnetic field points parallel to the area vector when it's actually perpendicular to the area itself, because the vector that measures the area is the normal, which is actually perpendicular to it. Let's draw a picture of what magnetic flux might look like. So we've got a loop which represents our area, and then we've got magnetic field coming through to pass through this loop. If we measure the loop by looking at its dA vector, that is the area vector being perpendicular to the surface and its magnitude being equal to the size of that area, the angle between this magnetic field and the dA vector then is going to form a dot product cosine. Because remember, the magnitude of that quantity inside the integral, in its simplest case, is just b times a times the cosine of theta. And that assumes that each are independent of the other, that the area, the magnetic field doesn't change as a function of the area. So it would be a constant magnetic field over the area, and then we'd just be interested in the angle between the b vector and the dA vector. Of course, if that angle is 0, because B is already perpendicular to the surface or parallel to the area vector, this would get even easier. And in the simplest case scenarios, we'd measure magnetic flux just to be the magnitude of the B field times the magnitude of the area it's going through. Now, when we looked at this last time for electric fields, of course, we were interested in a closed surface, because in Gauss's law, we wanted to capture every bit of the electric field. Of course, that electric field went radially, and it began at one particle and ended at another particle. Of course, we won't be interested in that for magnetic fields, because magnetic fields are loops. That is, they're continuous circles. Since there's no magnetic monopoles, magnetic fields don't start and end anywhere. They pass through space as continuous circles. So there'll be nothing like Gauss's law that attempts to sort of surround the magnetic particle and sort of measure the strength of the magnetic field as a result of the monopole we've surrounded. As a matter of fact, they actually call it Gauss's law for magnetism, and that is if I make this a closed loop integral of B dot dA, then this is guaranteed to be equal to 0. It's guaranteed to be equal to 0 because B fields are always full loops, which means if I encompass a closed surface around a loop, so the loop is contained entirely within the closed surface, well, then it guarantees that the loop never pierces the surface, and if that's the case, it causes no flux. But of course, if a field line pierces the surface in one location, it has to loop around and come back through the surface in another location, because again, this symbol means it's a closed surface, so it's something very much like a sphere. Well, once that's the case, every field line that pierces the surface must pierce it twice. And that means the negative flux and positive flux will be exactly equal to each other. So if I integrate over any closed surface, I must get 0 if it's the magnetic field I'm integrating over. So that's a true statement, which is called Gauss's law for magnetism. And it basically is a dead end. It tells us not to ever try and evaluate magnetic fields with a Gauss's law style approach. So why then did we go ahead and talk about flux in terms of magnetic fields? If it doesn't lead to a Gauss's law-like relationship, what is its value? Well, it turns out that if this loop that creates the area is actually made up of a conductor, then this magnetic field passing through the surface has the potential to cause a voltage and a current in that conductor. The problem is a static field won't do the job. It has to be a changing field. That is, a field that increases or decreases its magnitude over time. This is called Faraday's law. Named after Michael Faraday, who did early work on both electric and magnetic fields. The actual representation of the fields is three-dimensional structures. Faraday's law says the following. It says if we take the flux of a magnetic field going through any closed loop, then an EMF, that is a voltage, will actually arise as a result of the rate of change of that flux through that loop. So this is what it looks like. The EMF is equal to negative d phi, and of course this is a magnetic flux, dt. So at its essence, this is a rather complex mathematical construction. That is, the EMF in Faraday's law is the time derivative of a spatial integral. It's actually an area integral. So it's negative d dt of the integral of b dot dA. What saves this from being complex is generally this time derivative applies to one of three things. That is, there's really only three ways that Faraday's law gives us of providing a voltage as a result of a change in flux. And that is, the time derivative either applies to the B field. So again, Faraday's law produces change in three ways. Way number one is that there's a dB dt. That is, there's a change in field. This field passing through the loop could actually be a function of time, so that it slowly increases or decreases in magnitude. So nothing else about the measurement of the flux changes. It's a constant angle, it's a constant area for the loop, but the field happens to be a time function, in which case we are definitely going to get a voltage as a result. The second possibility is that the ddt applies to the area. It could be a dA dt, and that means the area is changing. And that could change in a couple of different ways. One, of course, is the radius of the loop could increase or decrease. That's actually rather rare, just because mechanically it would be hard to imagine a loop that can increase or decrease its size, especially if it's surrounded by some sort of conducting material. What more often happens is the B field only occupies a certain region. And if I were to grab a hold of the edge of that area, that loop, and lift it up or down, then I can move it into the region with the field or out of the region with the field, and therefore the flux would be the amount of field that's passing through the area would change. That doesn't change the field magnitude, it changes the amount of the area that's being impacted, and that's what this represents. Basically, dA dt would be a change in the area that the field is impacting. It wouldn't change the angle, it wouldn't change the magnitude of the field, it would just change the rate at which the area is being exposed to the field. This is a really common way in which Faraday's law generates current. The third one is a little esoteric, and it's the hardest one to handle because it involves rotational dynamics, and that is, it's going to be d dt of this part, the angle between dA and B. So it's going to be d dt of cosine of theta. What that's going to lead to is omega times the sine of theta. There'll also be a sign change here, but we're less worried about that. And of course, what's omega? Omega is d theta dt, and it's actually the angular velocity of the loop. For this third scenario, we have to imagine that the loop is on an axis and can spin on that axis. Of course, as the loop spins, just like my hand is edge on and face on to you, that's the flux that the field sees, is the degree to which the area is exposed to it. So if we rotate the loop within the field, we're not really changing the area of the loop. Instead, we're changing the angle that's part of the dot product measurement. This, unfortunately, is the most common way because, of course, in motors and generators, that's what's featured. The loop that actually has the magnetic flux flowing through it is rotating within the field. So it's exposing more and less and more and less of the area, not as a result of a change in area, but as a result of the change in angle between the dA vector and the B field. And that's it. These are fundamentally the three ways within which Faraday's law operates. The final aspect of Faraday's law, which we haven't really talked about yet, and that's this negative right here. Why is the EMF always the negative of the rate of change of the flux? Well, let's take a look at why. It has to do with conservation of energy. So let's imagine a loop of wire. And again, I'll put it so that this end is coming towards me and this end is going away from me. So this end's really coming towards you as the observer, but because it's leaving me, I've got an X there, and of course I've got a dot here representing that this end's coming towards me. Now this is just one of these flux loops, and let's imagine that that's a conducting wire going all the way around its edge. Let's imagine now that a magnetic field is coming up from below, and that the magnetic field is not only passing through the loop, but that its magnitude is slowly increasing over time. So do you have a mental picture of that? We've got a B field going up through the center of this loop. It's producing a flux, and it's of this variety. Number one, it's going to increase as a function of time. Well, what does that mean about the current flow through the loop? Well, let's just sort of go on autopilot and use the right-hand rule the way we always have. If you didn't know any better, here's what you'd do. You'd say, hey, my thumb is pointing in the direction of the magnetic field, and my fingers curl in this sort of counterclockwise direction into the board here and out of the board here. So that to me would predict that this is the direction in which the current would flow. It would go into the board in this direction and out of the board in this direction. So let's draw arrows to represent that. That's exactly how it would go. Well, here's the problem with that. The minute there's a current flow in response to the EMF set up through Faraday's law, as a result of a change in flux going through this loop, of course, now we have current flowing through a wire. And we know what current flowing through a wire does. That generates its own magnetic field. Not the magnetic field generating the current, but the current generating its own field. And of course, it isn't very difficult to determine that if the current goes in this direction, that would produce a field that would point upwards. So there's an extra magnetic field now generated solely as a result of the current. So we already had a B field that was increasing in the upward direction, which set up the current flow, which set up a new B field, which increases the flux, which increases the magnitude of the current, and you can see what's happening. Because we said the flux produces a current that flows in this direction, we get a runaway situation where energy is no longer conserved, where the current flow is generating an increasing B field, which generates more current, which generates more field. In essence, I could start this process with a puff of upward magnetic field, and then I could turn this off, and the system would be self-sustaining. Not only would it sustain itself, but it would forever increase and generate free current as a result of the induced magnetic field from the current inducing a larger current. And clearly, that can't happen. So that explains the logic behind this negative right here. Let's look back at this scenario and let's really do it for real. So the first thing I need to do is get rid of a couple of these lines here. So I'll be right back. Okay, now that we've cleaned up our diagram, let's take another look at it. Okay, we have this loop which goes into the board on this side and out of the board on this side. We've also got a B field that's going up through the center of the loop and is increasing in magnitude over the time. Now, in our previous analysis, the only mistake we made was on predicting the direction of the current loop because we basically followed our instincts. We used the right-hand rule straight away. And Faraday's law tells us not to do that. It says change the polarity of the natural inclination of the right-hand rule. If the direction of flux increase is upward, that would produce a current that would flow in this direction. And this tells me to reverse it. The current actually goes in the opposite direction. And let's see what the implications are for that. That means the current comes into the board on this side and it flows out of the board on that side. Well, what's this going to do? Wrapping my fingers in that direction, that means the current that's actually flowing through the wire is going to produce a B field that points down. So this will be the current that's generated by the flux, and the B field it generates will be in opposition to the B field that's actually generating it. Of course, what is that going to do? Well, as the current picks up steam, it's going to generate a B field in the opposite direction and attempt to reduce the influence of the increasing flux. That makes perfect sense. That's almost like saying, hey, I'm going to push on an object, and what's natural is for the opposing force to actually slow down that object's movement. Friction, very natural force. I push on an object and friction causes the force that tries to cause acceleration. As soon as I let the object go, friction brings it to a rest. In this situation, the induced current flow actually produces a B field which opposes the change that generated the current. This is a far more natural system where you don't get a runaway generation of current, in essence producing energy for free. This little piece here, just that portion of Faraday's law, is actually called Lenz's law. It seems funny, but the negative in Faraday's law has its own description. Lenz's law says anytime a flux, a magnetic flux, generates an electric current through an induced EMF, then the induced EMF will always be in a direction that opposes the change in field that generated the induced EMF to begin with. In essence, it's always a change in opposition, and that guarantees that conservation of energy will never be violated. Okay, we'll spend the next few days looking at applications of Faraday's law and Lenz's law. It seems like a lot all at once, but the individual problems that break these down are really quite straightforward applications.